So I'm James Pritts. I'm at the Czech Institute of Informatics, Robotics, and Cybernetics in Prague, CTU in Prague. I wanted to acknowledge my colleagues who also produced some of this work. It's Susanna Kukelova, a co-author, Victor Larson, and Andra Holm, my advisor. So today we'll be talking about robust estimation, in particular multi-model estimation in computer vision. And so the structure of the talk will be first an introduction to classical sort of approach for robust fitting in computer vision. Then I will generalize the problem formulation, and then we will speak about multi-model estimation, robust multi-model estimation. And we'll speak about then some state-of-the-art approaches, which in fact, I know many of you are deep practitioners, and I don't know deep techniques for this, and I don't know if they exist, in fact. And we can talk a little bit about that as well. I think it's interesting. Then I will talk about the specific problem context, which is this repetitive pattern finding. So I'll introduce the specific problem that I've worked on. In particular, I'll focus on the multi-model estimation task, but many of my publications are actually in the geometry aspect of it. But I think it's more appropriate that we talk about the robust estimation part for this type of audience. And then, if there's time, I will talk about, I'll talk about how a particular solution, which I think is very elegant and simple and works for the type of problem that's being solved. And then, if there's time, we can generalize that and talk about a solution that you can involve more constraints. You can put more constraints on the problem. So that's sort of the outline of the talk. So computer vision, so if you're talking about single model estimation and you're talking about fitting geometry to local features, which I'll introduce in a second, the classic approach is Ransack. And the idea is this, that you have a chicken and egg problem. What does this mean? So on the left we have a set of data points, and there is some line in the scene that generated the measurements, which you can see in the diagonal there. And then there's some other generating distribution that's generating the outliers. Could be uniform distribution, but you have some line, and the measurements are taken from that line, and then there's outliers that don't belong to that model, that weren't generated by the line. So in this simplest problem context, you have a two-class problem, a labeling problem, and the labels are traditionally called inliers and outliers. The inliers, of course, belong to the model that generated the line model, and then the outliers are something else, and you don't know either. So this is a chicken and egg problem. You don't know the labeling, and you don't know the regression. Of course, the line can be parameterized, slope intercept, or angle and radius, and r theta, and then so you don't know that, and you don't know the labeling. So how to approach solving this problem? The approach is this, is that you take the data, and then instead of sampling the parameter space, which is done in traditional sampling, you sample the measurements. So you sample, for example, this is the minimal sample, 2 points, of course. 2 points constrain a line. And so you sample 2 points in the measurements, and then you fit a line using those 2 points. And then you look at the error. So you look at, in this case, the distance to the line, and you see how well does the error, how is it consistent with the inlying model? And you have some inlying model. You assume that there's some generating distribution for these measurements. For example, it could be Gaussian. So you can test least squares, for example, to see what is the likelihood that these measurements match that line. But in fact, we use something simpler, some proxy measurement, which I'll describe in a second. What you do is you make the consensus set. So instead of, okay, so this is discrete now, discretizing it. You count the number of inliers that fall within some margin of a line. And this tells you how good the fit is, basically. So this is just, you're maximizing a utility function here, which is, in this case, the number of inliers that fall within the boundaries of this thresholded, this dashed line. And then you repeat this process. So you continue sampling, fitting, estimating consensus set, and you're maximizing this utility function. And then finally you hit something that is from the minimal sample that describes this data quite well of your inlying model. And you can say with confidence that this is the model that this is the inlying model, the model that we're searching for, given the parametric assumptions of the line, for example, line, but it could be a different model. It could be, yeah, we'll talk about that in a second, but more complex, of course. And this n, by the way, repeat steps 1 through 4 n times. The n is calculated dynamically based on some combinatorics, and we'll talk about that now. So the idea is that you calculate this n based on the ratio of inliers that you've found so far, because this gives you an idea of dynamically you're estimating the proportion of good data in your set of measurements. So you're dynamically calculating this n based on the best consensus set that you've made so far. So you have the number of inliers over the total number of data. So this gives you an idea of the combinatorics, which can get quite expensive very quickly. So if your minimal sample size is on the left, so it's 2, 4, 7, 8, for line it's just 2, but there are other geometric models that require more. And this on the top row is the inlier percentage. So you can see that quickly that the fewer number of inliers you are, the more samples that you require, the larger your n, to estimate an inlying model with a particular level of confidence, say 95% or 99%. In this case, these numbers were calculated with 95% confidence, but typically you set it at 99. And what this red box is for just one global model, in typical two-view scenarios. So I have 2 cameras, for example, and I would like to estimate, say, the relative orientation of planes or the relative orientation of the cameras with respect to each other in an uncalibrated setting. Then you have as many as 7 measurements or 8 measurements, or sorry, 4 or 7 measurements that you need, or it could be even 8 for 8-point method for fundamental matrix. And given the number of inliers you have, you can see that quickly this becomes intractable. In fact, for the fundamental matrix with only 15% inliers, you're looking at nearly 2 million samples to calculate at 95% confidence the relative orientation of, or this relation between 2 cameras. So the idea is that this is effective. Okay, this is the next slide. So Ransack has been beaten to death in the computer vision community. These are all the different publications, the names of the different types of Ransack variants that have been published. So this was, say, takes us up to around 2007-ish, something like this, 2008-ish, in terms of robust estimation of computer vision for a global model between cameras, between 2 cameras, for example, 2-view geometry. And you have, of course, all these variants. Ransack was from 1980, and they have different methods of analyzing the consensus set, error measures, sampling techniques. I would say there's such a variety to choose from. But in fact, only one of them, and this certainly list is not exhaustive, but only one of them, one recently, estimates the multi-model case. So in the scenario I gave with the line, you had 1 model. But now we're talking about, for example, this situation. Before we get to the multi-model case, I'm sorry, I have another example here, but so let's keep a hold of that, and then we'll talk about the multi-model case. But I wanted to say something about this particular, the complexity of the problem, even with Ransack. So the degrees of freedom to find the sample. So if you have a particular model, for example, a line, you know that you need at least 2 points to estimate the line. You can estimate it from more, of course, which is a least square solution, for example. But the minimal sample is what the minimum number of points you need to constrain the model. And as you saw from those combinatorics, it's important to reduce the number of samples during sampling as low as possible, to reduce the number of samples you need to find a good model. So the idea is that for the line model, it's easy. But part of my research focuses on finding much more complex models. For example, in my recent paper that we submitted to ACCV, we solved a system of polynomial equations. So the idea was that we're using particular features from the image. They induce some constraints on a model that describes the geometry. And this induces a complicated system of equations that must be solved. It's still minimal. It's the minimal number of points that need to be estimated to solve that model, but it's complicated. And it can be done quickly, though. So the idea is that reducing, one focus of the research on robust estimation is just to reduce the number of samples, of points in your sample so that you can deal with the combinatorics. That's not what we're talking about today. That's another line of research. But so this was example, the system of equations I showed you before, this was an example result of solving that. And what's remarkable is that we're given a distorted image of a building and radially distorted. So there's nonlinear lens distortion, and we want to generate a frontal parallel view of that scene plane, of that facade. And what's remarkable is that we only required 3 points in translation correspondence to do the affine rectification and the lens distortion, and then we required another 3 points in correspondence to do the metric rectification, which gives you this fronto-parallel view. And the idea is that if you sample cleverly, it can even be the same correspondence. So this is an example of a more complicated vision problem that is solved using Ransack. And here you have one model, which is this metric rectification of the scene plane. So now we'll talk about generalizing this problem and why Ransack does not solve this problem. And there has been a lot of recent research on this, in particular in graphical models. And I don't know, actually, as I said, like if some of you have some references on deep papers, I can tell you the ones I know, but I don't know what's been done with deep networks on this. So here's the idea. Now we have this is a simple case, of course. These are very simple examples. We have lines and circles, conics, in the lower corner. But now you have multiple models. And in addition, you have outliers in the background. So you have things that don't belong to any model. And the deal is, if you do this greedily, suppose you just apply Ransack in a greedy fashion, the inliers to, say, the blue line in this upper left corner of course, are colored in blue, but even the other lines look like outliers to it. So in that case, you have structured outliers according to the blue line, which are the other lines. And then, of course, you have this uniform distribution of just noise in the background. So you can see that already this combinatorial situation gets very bad, because for the blue line, what is for that line an inlier is a very low proportion of the total data. And now if you have a higher order model, which requires a large number of correspondence, this completely explodes. So in fact, as I said before, Ransack was used to approach this problem. One particular approach was this multi-Ransack, but it wasn't effective. It's known not to give great results, although it was a first approach. And one reason why is that suppose you set a threshold, for example. It's possible that especially if you go greedily, but multi-Ransack is more a global approach, but even so, that if you set an inappropriate Ransack, a threshold for Ransack, you will, as you estimate the lines, you will steal inliers from other lines. For example, at these intersection points, especially in this top right situation where everything is confounded. So if you have some inlier here in this orange line, well, as they intersect, the inliers from the green and the yellow and the blue, etc., all look like inliers to the orange line, and you will end up taking those points to the first model if you do this greedily, for example. So you need to have a global view of the data. You can't do this in a greedy fashion, and the first approach of that was this multi-Ransack. And these are simple models, of course. This is like basic geometry, and so already the problem is a bit difficult. And now we're talking about real problems. So, for example, in this case, we have a labeling and regression problem, and we want to estimate seam planes. And we have measurements, feature points on the seam planes, and they're color-coded. This is the ground truth. This comes from the Adelaide RMF data set, which is one of the data sets used to estimate, to measure performance on multi-model estimation techniques. And so you have these feature points that are extracted from the image. You have two views of the same scene. So the camera was moved with respect from left to right view. So there's some relative orientation between these two scenes. And you're in the uncalibrated setting. You don't know the internal parameters of the camera. And so your task is to find the scene planes, and that means estimating a homography, which requires 4 correspondences. So that's the set of homographies here, H1 to Hn. So I think there's 5 in here, scene planes. I forgot I counted, but I think there's 5 colors. But the idea is that with each scene plane correspondence, each color is an associated model, but you don't know these labelings a priori. You have these point correspondences. So you know, for example, that this top left blue point corresponds to that top left blue point over there. You have only a tentative labeling of those correspondences done by photometric matching. So you have these correspondences, x1 and x1 prime, which correspond to, for example, a blue point in the left image and a blue point in the right image. You don't know if that correspondence is correct or incorrect. So your task is now to estimate the labeling and the set of homographies that will generate this type of labeling, and also generate the mapping from the set of blue points in this image to the set of blue points in that image. And so this particular problem requires 4 of these pair correspondences. Now if you go for relative orientation of a general object in an uncalibrated setting, you're talking about the fundamental matrix, for example, if you make the most general assumption. So now we have images, left and right image, and we have a different model. These are just objects that have been moved around in the scene. And for this, in the uncalibrated setting, you need 7 correspondences. So already we're at that case where if you have 15% inliers, you'll need, for 95% confidence, you'll need nearly 2 million samples to estimate. And you can see that, of course, the inliers of one object there are a small proportion of the total data with respect to the other objects, even though you have many, and this is a very simple toy scene as well. So now you have some idea of the setting in the multi-view context. These are classic problems, and this is really what a lot of the multi-model estimation goes for, these classic problems. So what are some state-of-the-art techniques? Well, we already talked about Ransack and its failings. There's these preference techniques that are called like J-linkage and T-linkage, and these are agglomerative clustering techniques. And I won't go into too much of that. I played with them a bit. But because of the agglomerative clustering, there's a problem in that you have at least quadratic complexity. So if you have a lot of models and a lot of correspondences, it really gets too expensive. So they have some, there's other techniques you can use, like min-hash and so forth, to speed them up, but there are some complexity problems there. Really, the state-of-the-art, as far as I know so far, is conditional random fields and Dirichlet process mixture models. The difference between CRF and DPMM is that one gives a hard labeling during inference and the other gives a soft labeling. And of course there's advantages to doing the soft labeling, but then you have a much more complicated estimation to do, and there's sort of more automated frameworks to estimate, to do inference in a CRF. But even so, this is a difficult problem because, of course, some of us are maybe familiar with conditional random fields. And the idea is that you have to, the state of the art is something called Perl, and then there's this label cost thing that gives you model complexity. But the idea is that you have to solve the labeling and regression problem. So you do your inference of the labeling on the conditional random field, you get some labels, and then you do a block coordinate descent, and then once you fix the labels, you go and estimate, you regress your geometric models, and then you go back and forth between these two, and you decrease the energy of the conditional random field. This is a highly non-convex and not particularly fun optimization. I've coded it myself. Directly processed mixture models, of course, you have expectation maximization. You can go by sampling and you can do variational inference for these, but the issue is this, is that these are highly non-convex problems, and for EM, for example, you have, it won't work because, well, you can sort of, if you do expectation maximization, you can introduce more models that are there in the scene. But then they get eliminated sort of just by model assignment or soft assignment. So you have to sort of, you have some optimization where you have to get rid of some models, just as you do like with k-means, for example. But the idea is, and this is necessary, so for both techniques, CRF and DPMM, the idea is you throw a ton of models at the scene, far more than are actually in there. And you have, for CRF, you have something called a label cost that penalizes for model complexity, which is how many models are there. And for DPMM, you have a sparsity prior. And basically, you let these prior, well, CRF is not technically a prior, but you let these penalties eliminate the bad models, and it sifts through the bad models. And why do you need to introduce all these extra models? It's because the problem is highly non-convex. So you need many different guesses to really converge on something reasonable. And you can see some very simple situations here, which is we're estimating covariance matrices here with normally distributed data with different covariances. And you can see the difference between CRF and DPMM. The first row both do quite well. You can see that each, with 50 initial models, this is just 50 models, which is quite expensive in these frameworks. It converges to a good solution, and this large ellipse is the outlier class. So basically it took one covariance and blew up the variance, and that's the outliers. It's like a uniform distribution, basically. Although you can mix in a uniform as well, it's more accurate. But you see in the second case, they both perform differently. You see the difference between hard and soft labeling. In this case, you have 4 ellipses here, and sort of bimodally distributed, and you can see the solutions, neither one is quite right. And then in the second case, DPMM gets the correct solution, but this CRF, it doesn't do well. So you can see that it segments all these elongated ellipses correctly, but because of the hard labeling that CRF does, it can't disambiguate these. So it goes into a local minimum too quickly because it makes decisions on the labels versus keeping these labels as floating. So let's move on because there's more to do. So I will introduce, this slide is out of order actually, but I will introduce the problem that I'm working on. And the idea is that you have repetitive content in the image, and you would like to detect these repetitions, and then you would like to segment those repetitions. So for example, we have a scene plane here, and we would like to say that this particular content is repeated, and this particular content is repeated, just from geometry and photometry alone. No learning, this is just segmentation, completely unsupervised, using only very basic geometric constraints and photometric constraints. So to talk about this problem, I need to introduce the scene model. So if you have an image as input to the technique, the image is actually not the input. We take what's called a local features-based approach. So the idea is that you extract local features from the image, and in fact your representation of the image, what's inputted to the algorithm, actually looks like this. So these are different local features that are extracted from this image. And this is what is used going forward in terms of when I speak about the image, these local features. So what is a local feature? Well, briefly, you have the image and you extract some region of interest, salient region of the image. For example, on the left side, this orange contour is what's called an extremal region. And then you extract some differential geometry from this region. So you have a centroid and two extremal points. And then from this you construct an affine frame, and then you can do this matching, and it establishes geometry. So you have this geometry that's established from these local features. And now you can talk about geometric estimation because you have different points in the image that are in correspondence. So this is the single view problem. We're no longer in multi-view, we're just considering a single view. And you can see that using this, we can establish correspondence between the same triple of points. This affine frame is simple, a 3-tuple of points. And then we get some normalization where we do an embedding. So we embed this feature into a descriptor, and then we're able to match them. So the idea is that you get some region, you describe with an affine frame, you embed it, and then you can cluster them. So you can label things as all blue or all pink, etc. And what can we do with this? Well, as I showed you in the image before, you can, for example, estimate the radial distortion using constraints. So the input image was on the left side, local features were extracted, and we undistort the image with radial undistortion. And the idea is that you use this constraint here. Well, I won't go into this equation and so forth, but you have a distorted features in the left image, and you can make them so that they're linear in the right. So the idea of this technique is, for metric rectification, is that you have some perspective view of the scene plane, and distorted, by the way. So this doesn't have a distortion in it, but you're looking at some perspective view of the scene plane. And you estimate, and our minimal model is this. We're talking about minimal samples. We have a metric rectifying homography H. And so the scene plane is rectified. And now if you see you have the perspective view and you rectify to this view, what you have is you've restored invariance of the scene. So in real life, of course, if you're looking at a scene plane, if something is repetitive, it has the same length, it has the same area. These invariants are restored after rectification. So what we do in this framework is that we estimate some metric rectifying homography, we restore the invariance, and then we can see what is matching in this rectified space for all measurements. So this is where we do the verification step of Ransack. So here's the pipeline. So input image comes in, features are extracted. These are all the features just from this dartboard, for example. So we have these features extracted. We find some minimal sample. In this case, it's three pairs of 2 correspondences of these local features. And then we get the results. We get the undistortion at the top, and we get the metric rectification of the dartboard. So now it looks as if you were looking at it frontal parallel. We've synthesized a frontal parallel view. But there's a big problem with this, and I'll explain. Because the idea is to get this nice rectification, we have to basically generate the pattern in rectified space, print it into the image, and do a maximum likelihood estimation. So we need some model of this very look how many features we have. We don't know the relation between all these features. We need some model in rectified space to print back into the image. It's a generative model, so we're basically, just as a line you would have as a model and printing it into the image, now we're actually printing the pattern into the image and estimating least squares distance from this model that we create. But we need some way to create the model, and actually it's quite difficult. because if you look at, for example, in the rectified space, these features, so that's the same features in the second panel. Now we have it in rectified space, so you can see that the invariants have been restored, a congruency, for example. You can see that there are many ambiguities. You can have a rigid transform between each of these correspondences. So as this thing repeats and a dartboard has 20 repetitions, you have a rigid transform between each of these repetitions. But it's not unique. You could, in fact, choose many different rigid transforms to overlay these features on each other. And in fact, this is supposed to be, so just for one group of these features, for one color, if you choose 20, like you have 20 correspondences across the dartboard, you have 190 models to choose from, just from one of these, and we have 100 of these or something like this. So each one of these induces some rigid transform that we have to choose from to represent the model in the image. So we have a model selection problem that's very difficult. So this is where the multi-model estimation comes in. And by the way, these are very nice images. This is not in practice, of course. These are sort of toy images, but in real life, you don't have these nice correspondences. You have all kinds of image artifacts. So in fact, the correspondences in this image are not rigidly transformed in such a nice repetitive way, in such a how to say it, there's not this frequency occurrence here that they're continually going. You have just sort of arbitrarily rigidly transformed features. So you don't know what these rigid transforms really look like just from the image. Like they can be quite noisy because of JPEG artifacts or misdetections and so forth. So that's what is represented on the right side. On the left side is represented the input of the method, and it's quite robust. The method I'll quickly present because I'm running out of time. But here we have the image on the left, and on the right is using just these inliers that were detected. We were able to undistort and rectify this image. Now, I will quickly talk about how I do the multi-model estimation, which is a simplification of what is done from the state of the art, but is necessary because, as I said before, we have so many candidate models, we can't use these more expensive techniques. So I'm going to introduce the set cover problem, which is quite simple. This is a classic problem in computer science. So it's just to find the minimum number of subsets that cover all points. So we have a set of points, we have a set of subsets that cover those points, that the points are members of, and we want to find the minimal subset. So of course, this is not minimal, but it does cover all points. In fact, this is the minimal subset for this set of points. So we want to choose this. That's the sort of problem formulation of set cover. Now, we would like to do this for our geometry problem. So the idea is we have our correspondences in the image, which are represented by the points, and we have some model that the correspondences are inliers to. So you have some geometry such that this is the model, and you have the inliers in the Ransack context. So these particular measurements in the images, these correspondences, are inline to that model. So in that sense, the model covers those points. And we want to select the set of geometric models that cover all correspondences that are inliers. So that's how you can sort of use the set cover problem to solve this geometry problem. And so how do you do it? So the idea is that you have your models are represented on the top row. So these are different, for example, in the rectified space, this would be your rigid transforms, and there could be hundreds of them, for example. And then your correspondences are along column-wise. So these are the points that are can be rigidly transformed on top of each other. So, for example, in this first row, you have a distance of 5.4, which means that if I take two correspondences and I rigidly transform the first onto the second, then there's a distance of 5.4 between the points of that correspondence. And so you can create this matrix using the particular model, what distance is induced by using that particular model to correspond these 2 points, to map them on top of each other. And what's interesting is that, let's forget that, let's apply the Ransack threshold. So now we apply some threshold of what is an inlier. And you get this binary matrix, which tells you which models describe which points the best. Okay? Because now we've just thresholded them. And you can see that these two columns on the right side are describing most of the points the best. Like you can choose some of these other models, but these two are the best candidates to describe some subset of the points in this set cover formulation. So the idea is we can choose those models with a matrix vector multiplication. We just set these last two elements in this vector, and this selects those two models that are describing those points. And the idea is this, that this vector is what is selecting the models that are describing our data, and we want to enforce sparsity on that vector. So if we enforce sparsity, we are naturally having a parsimonious description of the scene. And so the idea is this, is that we do this through integer linear programming. So the idea is this vector W is what is choosing our models from the candidate models. And we want to enforce sparsity, so we want to minimize the zero norm, and which is just the number of non-zero elements in W. And then we want to make sure that this constraint makes sure that every point is described by some model in our inlying set of points. So we know that all of these are inliers to some model, and we want all such inliers to be described by at least one model. And that's that second thing, second constraint. The first constraint, I'm sorry. But this is an NP-hard problem because this is integer linear programming. Set cover is known to be NP-complete, and the optimization problem is NP-hard. So we relax the problem. And instead of minimizing the zero norm, we minimize the one norm. So now we can enforce sparsity because we can this is a problem we can minimize with a linear program. So instead of having binary variables, we have continuous variables, real variables. And instead of minimizing the zero norm, we minimize the one norm. And I will skip this because we're running out of time. I guess we have 5 minutes left so we should start questions soon. So let me skip this a bit. The idea, though, is I'll talk briefly over this slide, which is that this is actually just a very constrained energy minimization problem that we've just done. So this is the problem formulation for the uncapacitated facilities location problem. And the problem we solved is a simplification of this. So in fact, we could include other energies. We could include other potentials. Like this term over here is like the unary term in an energy minimization term. But the two green elements are the problem that we minimize, basically. And if you generalize the problem more, you can include other energies, for example. And if you generalize it even further beyond the uncapacitated facilities location problem, you can do minimization with data terms, with regularization terms, and model complexity terms. So the idea is that this is a simple implementation. You can do very fast construction of your candidate models and inlier sets, and you can feed this to a fast linear program solver, CPLEX. And the CPLEX because it's extremely well engineered, it will give you a solution to very large problems in milliseconds. And this was the idea of this task, was that of course you can use these other models, which I introduced earlier in the talk, for example CRF, but they're quite expensive. And because we're testing so many models, and because we want this to be reasonably fast, this process, this frontal view synthesis, we chose a different problem formulation, and we solve it with a linear program, which is fast. And does it work? Yes, it does work quite well, in fact. This is a very ill-posed problem, and we get very good results for this. So for example, here we have a rectification so the scene plane, for example, is the side of the train, and we're able to generate a frontal parallel view of the train, and we have a ton of motion blur. We have JPEG artifacts, really low quality image, and it works quite well. If you look at the features that we got out of here, it's quite a good result. Then we have extremely wide field of view. So we have this Chinese entrance gate, and then we are able to get the undistortion, and we get this frontal parallel view from very few features. And we're using the method that I just presented, or at least part of the method I just presented. Here are some more results from the recent paper. So these are image triples, so you have quite large lens distortion, you have patterns in the image on planes. On the top right, top left you have the input image, top right you have the undistortion, and bottom you have the rectification. And also, because we've done this model selection, you can find out where the symmetries are. So here we color the rotational symmetry. We have an 8-fold rotational symmetry that we were able to label in this technique. And then we can do the segmentation. And what's really cool is the segmentation is very precise. Why? Because, well, some people say we got lucky, but we have this blue segmentation for the 8-fold symmetry. And if you notice, the 5-fold symmetry in the center is not blue. So we were able to disambiguate the 5-fold symmetry from the 8-fold symmetry. Okay, and I'll skip this part because this is a more elaborate formulation, but I think we can end the talk there, so we can have time for questions. Thanks.
James, thank you. Questions first.
Hello. Yes. Thank you for your talk. The first question is, as you know, in recent papers, it's common to use deep learning features on top of the classical computer vision algorithms. Why did you use the safe descriptors and not CF descriptors are not the features generated by deep learning model.
Yes, that's okay. First off, the method is agnostic to the type of embedding or the features extracted. But you're exactly right. Like in fact, Yaroslava has been playing with some deep features at UCU. So we are looking at LFNet. We're looking at AFNet. These are recent deep features papers. The short answer is just time. I haven't had time to try it because you have quite a large pipeline. So playing with the input can cost you lots of time to see what parameters need to be changed, etc. But another thing is that it'll be interesting because classical features are based on geometrical principles. So they are designed with certain geometric assumptions. So we know that the geometry we're getting from them is reliable. With learned features, it's unclear what geometric constraints were used to learn these features. So I am curious to experiment with them and see if the learned features do represent, they can be matched well, it's clear, and so forth, but do they produce reliable geometry estimation? Because they, of course, are highly parameterized, these estimates of both the geometry and the embedding. The embedding is clear, is good, but for the description, but for the actual geometry estimation, it's unclear like what was learned there and what is being represented in terms of this geometry. But I'm curious to find out. But the method, you could replace it with the front end, any local feature you could choose and run the same thing through.
Actually, you could train the features if you have if you know the correspondence, you can train the features of a model too.
Yes, and in fact, you even have, since you have the rectified view, you have what those patches look like in rectified space. So you're exactly right, and that's work that we plan to try to pursue. So.
Okay. Other thing is, there is unlucky security for model selection. There's only one model. I was reading with a Hoff lines. Is it possible to discretize the space of the models, like lines, and
of
make
course.
every point to vote for the line?
That's correct. Like you can use the Huff space, so you can. This is voting for parameter space. So, but the problem, there's a big problem with that because suppose you have a complex model, like a homography, for example. Already, what is your parameter space for homography? So for Huff space for lines, it's 2 dimensions. But the Huff space for a multi-view relation that's complex is much higher. Secondly, you don't, and this is a classic problem in computer vision, you always try to measure in the image space. You never try to measure in the parameter space, because what is the distance in the parameter space? Like, it's not always possible to see how are things close in these parameter spaces. We would rather reproject into the image somehow and measure distances in the image, because that you know what you're dealing with. You're dealing with pixels. But if you're trying to, in a complex model that may be modeling some projected geometry, it's unclear if even a parameter that looks close in this space may actually produce a very large distance in the image space once you use it in your fit. So I always try to avoid methods like Huff or parameter space clustering. I have used mean shift, for example, for this problem, but I try to avoid it because we don't know what distances we're dealing with out in space. It requires some training, for example, to really disambiguate what these distances mean.
Hello,
Yes.
James. That was very interesting. My question about your correspondence matrix and energy function. I want to know, do you consider some options for regularization, like eliminate linear dependencies with your features?
So you're asking about some regularization energy? Then?
Yes.
Yeah. So that is a big problem with this technique it's a very good question. The problem with this technique is that it is strictly unary and model complexity. So we have some way to select for models, we have some way to test unaries. But if you want regularization energies, you have to go to a more complex representation, which I have here, but I didn't have time to talk about. So now, because basically you can reduce uncapacitated or polynomially reduce uncapacitated facility location to set cover, and you can reduce CRFs with a data term, regularization term, and model complexity term to uncapacitated facility location. So they're all NP hard, and this is the most complex formulation. Is the one you're talking about. If you want to add regularization energies, add model complexity energies, add unary complexity, and that's state of the art, or very recent. And one comment about state of the art, for deep networks, I know, for example, but just 2 recent publications that have done end-to-end correspondence finding, multi-view geometry estimation, and sort of output. And they are basically at a very early stage in the sense that they're estimating one global transformation between these 2 images, not multi-model. And they've just gotten it robust. For example, there is a paper by Pascal Fall's group at EPFL and one by Intel. And they are figuring out how to encode robustness into this deep network to regress these two-view parameters. And they're able to do it just for one image, and it's unclear, I haven't played with them how well they work, but one of my colleagues says it's very interesting work. But for example, the Intel group figured out how to do basically iterative weighted least squares inside a deep network, which is quite interesting. Hello, Tanya.
I have a more question about application. Have you looked at distortion and missing values, like overlap by shadow or something? If you have several pictures with such problems and you want to reconstruct not only the view but also some partial data on the image, have you looked at that?
Sure, so occlusion is a classic problem, and that basically generates outliers. So if you have occlusions, then for one thing, that's the point of the local features approach, because basically dense matching has replaced almost everything in deep networks, except for our little guys in geometry, where we're still holding out against the deep guys. Local features, that's the point of the local features, is that you locally describe the image. So in an occlusion, locally that data will be missing. There will be no local features there in one image. In the other image, they will be there because it's not occluded. And what happens is then those correspondences become outliers. There's no correct correspondence for image in right versus the image in left, which is included. So those will likely get matched to something wrong. And then in your correspondence set, those will be outliers. And then you need the robustness of these techniques to filter those out. And that's the classic approach.
Please, applause for James. James, thanks a lot.